Hello everyone, and welcome back to the channel. Today, we're diving deep into the mind of a Nobel Prize-winning genius whose work you probably interact with every day without even realizing it. We're talking about Leonid Kantorovich, a Soviet mathematician and economist who revolutionized how we think about efficiency. Let's start with one of his earliest, yet most groundbreaking works: Mathematical Methods in the Organization and Planning of Production. Written in the late 1930s, this wasn't just a book for math nerds. Kantorovich was speaking directly to engineers and factory managers. At the time, Soviet industry was under immense pressure to hit ambitious targets with limited resources. Kantorovich's genius was to show them how to turn their production challenges into a clear mathematical problem. He introduced the concept of linear programming, framing production as a set of constraints, like how much raw material you have, and an objective, like maximizing output. This was a radical idea, using math not just to describe the world, but to actively optimize it. This practical approach culminated in his major work, The Best Use of Economic Resources. Here, Kantorovich made a powerful, pragmatic argument that transcended ideology. He said, "Look, it doesn't matter if your economy is capitalist or communist. Resources are scarce, and we should allocate them based on transparent, logical calculations." He introduced the idea of shadow prices. These aren't real prices you see in a store. They are calculated values that tell you the true worth of a resource within a system. A high shadow price on steel, for example, signals a critical bottleneck. This information empowers a factory manager to know which material to conserve and tells a government minister which industry needs investment the most. It's about making smart decisions based on real scarcities, not just guesswork or political whims. One of the most elegant applications of his ideas was the transportation problem. Imagine you have goods in several warehouses and you need to ship them to various stores. How do you plan the routes to minimize total travel distance and cost? Kantorovich created algorithms to solve this puzzle. His method was about equating the marginal cost of transport with the marginal value across the entire network. This makes waste incredibly visible. Think of it as finding and eliminating unnecessary detours on a massive scale. This single idea became the foundation for everything from scheduling freight trains and managing pipeline flows to how modern digital platforms balance server loads. The delivery app that brings you food. Its efficiency owes a debt to Kantorovich's work from decades ago. So, what gave Kantorovich this unique perspective? It was his deep background in a field of pure math called functional analysis. He saw economic problems through the lens of convex sets, linear operators, and dual spaces. This might sound abstract, but it allowed him to define problems with incredible clarity and produce claims that could be rigorously tested and verified. This mathematical foundation also enabled him to connect with parallel developments happening elsewhere in the world, like John von Neumann's game theory or the Kuhn-Tucker conditions in optimization. He was building bridges between seemingly separate fields of knowledge, and those bridges led to some incredible places. Kantorovich's work on optimal transport, for instance, took a giant leap. He extended the idea of moving physical goods to moving abstract concepts, probability distributions. This created a way to measure the distance between two different statistical outcomes, defined as the minimum cost to transform one into the other. He couldn't have known it at the time, but this concept, now known as the Kantorovich-Rubinstein metric, is a fundamental tool in modern machine learning, image processing, and AI. The mathematical seed he planted has blossomed in fields he never even worked in. But Kantorovich wasn't just about theory. He and his team rolled up their sleeves and applied these ideas to real-world industrial problems. They went into timber mills and used linear programming to figure out the absolute best way to cut logs to maximize usable plywood and minimize scrap wood. In metallurgy, they developed models to create the most cost-effective alloy mixes while respecting capacity limits. These case studies proved that math wasn't just an academic exercise. It could save massive amounts of resources, slash delivery times, and help align the goals of a single factory with the needs of an entire nation. So, If we were to boil down Kantorovich's entire philosophy, it would be a mantra of disciplined planning. No plan without a model, no model without data, and no decision without a price. He never claimed that his shadow prices could solve complex political disagreements. Instead, he argued that they make the trade-offs clear. They force you to confront the real cost of your choices and prevent catastrophic waste. In any economy struggling with scarcity, which is to say every economy, he believed this discipline wasn't just a technical advantage, it was a moral imperative. Let's look at two major areas where his influence was profound. First, within the Soviet Union itself. During the 1940s and 50s, Soviet ministries were constantly dealing with production bottlenecks. Kantorovich's methods weren't just theoretical, they offered immediate practical solutions. We already mentioned timber and metallurgy, but his work on transport was also huge. By optimizing routes for trains and river barges, his models helped reduce the amount of time goods spent sitting idle in warehouses, dramatically speeding up the entire supply chain. These weren't just small pilot projects. They became standard operating procedures for managers under pressure to deliver. The key lesson was that centralized planning could be made smarter and more responsive by using consistent shadow prices to guide thousands of local decisions, aligning them with national goals without micromanaging every single action. Second, and perhaps more surprisingly, was his impact on the rest of the world. Outside the Soviet Union, linear programming became a cornerstone of a new field called operations research. Capitalist firms eagerly adopted these techniques. Oil companies used them for refinery planning, airlines for assigning aircraft to routes, and retailers for deciding where to build new warehouses. Public agencies also got on board, using optimization for everything from designing nutritious, low-cost school lunch menus to planning emergency logistics for disaster relief. As computing power exploded, the scale of problems that could be solved grew exponentially. The language of Kantorovich, constraints, dual variables, slack, became standard in business and engineering schools worldwide. Today's hyper-efficient global supply chains, with components crisscrossing continents, are simply unthinkable without the optimization calculus he pioneered. In a fascinating twist of history, his method escaped its Soviet origins and became a universal tool for efficiency. Of course, no revolutionary idea goes unchallenged. Kantorovich's work faced its share of criticism. A major one was the linearity assumption. Critics rightly pointed out that the real world isn't always linear. Factories have economies of scale, and workers get faster with experience. The defense is that linear programming is a powerful first approximation. It's the starting point, and it can be refined with more complex techniques to account for these non-linear realities. Another big debate centered on information. Critics in the West, inspired by thinkers like Hayek, argued that no central planner could ever gather all the necessary local information to make an optimal plan. They believed decentralized markets and local incentives were superior. Kantorovich's clever response was that his shadow prices were precisely the tool for decentralization. If every manager in the system faces the same accurate price signals reflecting scarcity, their self-interested local decisions will naturally align with the global optimum without needing a direct order from the top. Then there's the problem of a changing world. A static plan, no matter how optimal, can become useless overnight if conditions change. This is a valid point. The framework has since been extended to handle uncertainty and dynamic, multi-period planning. But these advanced models require even more data and computational power. Critics also pointed out that shadow prices are only as good as the data you feed into the model. If your accounting is flawed, or your production targets are politically motivated rather than based on reality, the resulting optimal plan could be disastrous. This isn't really a flaw in the math itself, but a crucial warning about the importance of good governance and accurate data. The politics were also tricky. In planned economies, his ideas were sometimes viewed with suspicion, seen as a backdoor to introducing market-style thinking. Meanwhile, in market economies, some saw this kind of large-scale planning as technocratic overreach. Kantorovich always insisted his method was neutral. It doesn't care who owns the factory. It simply asks, are you using your resources in the most valuable way possible, according to your own stated goals. Finally, there was the risk of the models themselves. Large, complex models can be fragile. A tiny error in an input number could lead to a wildly different and wrong solution. This is why Kantorovich was a huge advocate for iteration and stress testing. A model isn't a one-and-done solution. It's a living tool that must be constantly updated with new data and tested against different what-if scenarios to ensure its recommendations are robust and reliable. Leonid Kantorovich gave us a new language for talking about efficiency. His work shows that by framing our challenges with mathematical clarity, we can find better, smarter, and less wasteful solutions. From your Amazon delivery to the global flow of goods, his legacy is all around us. Thank you so much for watching. If you found this journey into the world of optimization interesting, please hit that like button, and don't forget to subscribe for more deep dives into the minds that shaped our world. See you in the next video.